So for Newton's first law of motion, it is the same as it was last year. I'm going to add some terminology to it just so you know what the terms are when they pop up and what it means. Alright, so for Newton's first law of motion, you also known as the law of inertia. That's Okay, so the first one we're looking at is the first law of motion. I had it on mute here, so I just have to repeat for Olivia. So we have our two new terms, static and kinetic equilibrium. Equilibrium, remember, means balance. So when we look at objects in equilibrium, we're looking at all the forces on them are balanced. Okay, so we're going to be looking at this a lot over the next unit. We always come back to it because sometimes the whole object in both two dimensions, like vertical and sideways, will be balanced. Sometimes it will be balanced in one dimension and not in another, so it will only accelerate in one dimension. So the word static, where did my markers go? Right there. So when you're looking at the word static, you remember that static just means at rest. Right? So when we look at static equilibrium, right, that's an object Alright, so an object at rest is static equilibrium, so it's not moving, all the forces are balanced on it. So technically you're in static equilibrium because all the forces on you at this moment are balanced. You're not moving, you're stationary, the normal force is balanced out with the force of gravity, and that's it. Right? You don't have friction acting on you right now because you're not trying to move anywhere, you just have two forces. For kinetic equilibrium, it's your an object in motion, right? But again, all your forces are balanced on it. So if you're walking at a constant pace down the sidewalk in a straight line, you would be in kinetic equilibrium because your force that's going forward from your shoes balances out whatever forces are pushing back on you, so you get to go at a constant speed. Right? Same thing as if you're in your car and you say you're going straight out to New Hamburg, and on the expressway, if you set your car in cruise control, if you're going straight, then you're in kinetic equilibrium, so everything is balanced. Right? So that's what we're looking. That's our focus today, is being in balance. This meme there at the top, right? The first law forgotten. So you can see that this truck was carrying a huge load of, I have no idea what that is, right? But it was not fastened down anywhere inside the truck. So when the driver slammed on his brakes, his truck stopped because the brakes are attached to the truck. But whatever he was carrying is not fastened down. So it was in kinetic equilibrium, and its inertia kept it going forward. So that's why it burst out of the container that it was in. Right? So if you're not held down, your body, it's called the law of inertia because your body wants to keep on doing what it's doing. Right? So if it's like the box here or rock or whatever that is, right? It kept on doing what it was doing. It was moving at 20 meters per second forward. When the truck stopped, it still wanted to go 20 meters per second forward, and nothing was holding it back, so it crashed into or out of the truck. All right, are there any questions with this slide? Are we okay with Newton's first law of motion? So it's about being in balance and things keeping or wanting to keep on moving the way they're going. So that's the end of my note for Newton's first law of motion. There you go. It's not easy. Trust me, it's not easy. It makes it look easy because I only wrote a couple lines.
This portion of this is like considered like the easy like unit. So that means it's right.
Everybody's different.
Okay.
Normally, traditionally, my students find energy the easiest.
The Well, are we done yet? Are we doing it after this?
Yeah, that's next week. Okay. The other way to, I should write this down before I go to the next question. The other way of doing this one, or other notation, remember we started this on the other day, that we have the net force on the object is equal to 0, which is the mass expression for Newton's second law, or first law of motion. So when your net force is equal to 0, your object keeps on doing what it's doing. Could be at rest, could be moving, it just keeps on moving. Or at rest. Okay, so if you guys are good with this theory, I really wanted to focus on the math today because the math is not easy. And we'll see how far we get. Because it's really just like what you did on your homework on Friday, which you probably haven't done yet. When we look at the net force, but your work on Friday was calculating net force for different scenarios. Now we know the net force is 0, so we're going to find things that kind of balance out. So if we read this question here, Chu's not here today, but he's standing on a slack line that's tied between two trees, like in the picture there. Has anybody done slack lining before? Something that I would like to have over top of my pool. I always thought it would be cool to try to go across the pool on a slack line, but I've never tried it. I think I would fall. But so the slack line is just like a tight rope. You can sometimes see the people in parks using it because it comes in a kit. You just ratchet it against two trees and then you just try to walk between the two trees. And the better you are, the higher off the ground you can go. So for this example here, we have two standing on the slack line, as you see. The angle, we have some angles involved here, and we want to find the tension on each side of the rope. So this question here, in terms of level of difficulty, this is the harder end of these questions, because the easier end is that the angle that it forms is equal on both sides. So if I flip ahead a slide, which we're not going to do, you can see in this example here, right, the angles are the same, so that makes this question easier than the one we're doing. Okay? So does everybody understand what's happening in the question? You have a person standing on a tightrope, period. Then we want to find how much each rope, the tension in each rope. So here we go. I'm going to just move my camera across the way here. Perfect. Alright, so here's my system diagram. I have two standing on the slack line between two trees. So the diagram is pretty simple. There are no kinematic vectors because we're not moving anywhere. We just have this. Okay? So the harder part, or I guess I can put the angles in too. So this is going to be 50 degrees over here, and this side is going to be 30 degrees on that side. So the longer side is 30, the shorter side is 50. So the free body diagram for this scenario, so I'll just do underneath here. I have the force of tension going one way, right, because it's up the rope towards the tree, and the force of tension going the other way and the force of gravity went down. Alright, so we draw our diagram, we have our three forces because gravity is always there, and we have our components because things are on angles. So take a moment, draw that down, close my email so it stops pinging at me.
What's the force going to the top left?
We have FT1 and FT2. Because they're both tensions, right? FT is tension, and there's two ropes, so I have T1 and T2. Sadly, there's no easier way to write that. Sometimes, actually, in textbooks, you might see like just T for tension, but it also stands for temperature and period. So I try not to use it. That just adds to a confusion with the same letter. Everybody with me? Any questions? We have a lot of unknowns, right? We don't know FT1, we don't need FT2, we don't know FG at the moment. All we know in our table values, which is a nice simple table of values, is that we know the mass is 50 kilograms. So these formulas, right, that we're going to use are not found on your formula page because they're all like pieces you're going to be putting together. Right? It's a puzzle that you have to figure out. Okay, so next stage is that we need to recognize that this is a 2D problem. Right? So we have, just like in projectile motion and everything else we've done, right? We have two dimensions. So I'm just going to split my board into two here. So we have two dimensions. We have the X dimension and we have the Y dimension. So in this case here, it doesn't make sense to rotate my coordinate system. So I'm just going to use the normal, like what I classify as normal or a regular Cartesian plane, because there's nothing up there that's perpendicular to another one, so it doesn't really cut down on any work. Which direction would you like to start in, the X or the Y? We're going to use both. Jake, what would you choose?
Probably the X.
Sure. There's no right answer. Whatever you want. Okay, so for the X, we have our net force in the X direction is equal to 0. So the net force in the X direction is equal to 0. So we have to look at our diagram here. So there's different ways to write things down. So I'm going to do it a little bit different than we did in our last unit. So if we look at our X direction and my compass system, which force in the X direction is positive and which one's negative? So you're going to match it up with your coordinate system. Which one's positive, Anne?
FT1X is positive.
Good. So FT1X is positive, right? Because this direction I said it's positive. So I'm going to write down FT1X. And I'm going to subtract FT2X. So I put the minus sign in there because they're in different directions. If that doesn't make sense to you, please do what we did before. And don't write this down, this is just optional. But you can also write it down as FT1X plus negative FT2X. Either version works. It's just a matter of what makes sense to you. So pick a mode and stick with it. I'm going to do the top row just to do something different, just to give a different point of view. But feel free to do the bottom row there. Either one's right. So here are some issues. Maddie.
How do you know when it's going to be 0?
It's a great question. So in this case here, to standing. So if he's standing, he's not moving. So that's static equilibrium because he's still. So everything's balanced. If it was kinetic equilibrium, it would say he's moving in uniform motion or something along those lines. So that's why it's 0, because everything's balanced. And that's the theme of this topic, so that's another hint. But does that make sense? Okay. So if we look at this, here's our problem. Is that we have FT1 cosine 50 minus FT2 cosine 30 equals 0. Right? So we have two unknowns here. We don't know FT1 and we don't know FT2. So we have to stop. We can't go on. So what we need to do is be good mathematicians, and we have to find another equation that has both FT1 and FT2 in it. So that's why we work in the second dimension, in the y dimension, because it also has FT1 and FT2. So let's flip over there. So I will do this. All right, so it's balanced in the vertical direction too, right? Because he's just standing there. And what do we have? We have FT1y plus F2y. So in this case here, we have the two tensions that are both going up, but we also have gravity going down. Right, so that's going to cause a problem there. We have two ups and a down. So if we do some of our math magic here, we have FT1 sine of 50 plus FT2 sine of 30 is equal to FT. All right, so I brought the FD over, put in the angle stuff for the two vectors.
Can't we find the force of gravity?
We can. How do we do that?
Mass times gravity?
Perfect. Awesome.
Why do you move gravity on the other side?
That's a great question. So I moved over to the other side because it was -1, so I want to make it positive. And the second reason I did it is because in my head, I like to move the constants that don't have any of the variables that I need on one side. So I can work out it's going to be a number, so I can keep it by itself. I want you to keep in mind, as Andre pointed out, though, that I know all of you think differently than me, so do what makes sense to you. Where we're going with this is that you can see we have the two unknowns here, we have two unknowns here, right? So we're going to have to do some substitution here. We're going to have to solve, I'm going to choose this one because it's easier, solve this one for, let's say, FT1, and then we're going to put it in for FT1 over here to find what FT2 is. Okay? So this is not an easy question. But here we go. So if I take this one here, and I'm going to rearrange it for FT1, right? I'm going to take the cosine over the other side, so that's going to be FT2 cosine 30 equals FT1 cosine 50, and then when I divide each side by it, I think it's something that looks like that. Alright, so just find FT1 by itself. Okay? So I'm going to call that equation number 1, just because it's going to be significant. We're going to come back to it in a second, so I can find it really quick. Let's call this one equation number 2. So where we left off on the y dimension. So what I'm going to do here, and I'm going to write down sub 1 into 2. This is where it gets a little tricky. Not tricky already.
Sorry, Cal, for the first question on the left, you forgot to write 0, right?
Pardon?
You forgot to write 0, right?
Where?
Or 30 below.
Thank you. So we do the substitution here. So it's just getting nastier as we go, right? It's longer, not very easy. How can I simplify that line? There's one thing I can do to make it a little bit less intimidating. Hunter?
Divide by FT.
Okay. What's the trig ratio that's up there? Yeah, see it? It makes it a little bit easier. Not much, Jake.
Like the sine 50 and cos 50 become tan 50.
Yeah, good. So we have sine over cosine here, which you might remember as tan. And if you don't remember as tan, don't write this line down. It's up to you.
Even if you just calculate sine 50 cos 30 and move it to the other side, grab it. You could probably do a lot of things here. Like there's probably a lot of ways to do this.
Okay? So we did our sine over cosine, so that becomes tan. So I got rid of the fractions, I don't like fractions. And then what do we do next?
Oh,
Alex?
I'm just asking with the previous thing. Couldn't you just move in the sine 50 and multiply the cosine 50 by sine 50 and get like an actual number?
If that makes sense to you, do it. But then you're rounding earlier and your answer won't be as good as mine. What's the next step here? What other math skill comes into play? And?
You can factor out FT2.
Good. So now you can see that FT2 is a common factor between these two terms. Right, so we can factor that out.
This is math class. I'm back in grade 11.
So we can factor out an FT2 because it is a common factor there. And then we just take the bracket, that number, as Alex pointed out, it's just a number after all, and move it to the other side. Andre?
So just for clarification, you get tan by sine divided by cos or sine multiplied by cos?
Sine divided by cos.
Yeah, okay.
Yeah, your trig identities, right? Sine theta over cos theta equals tan theta. But if that doesn't make sense to you because you don't like trig identities, then don't do it. Like, you can do whatever you want. You can be Alex and put in numbers all the way through here, and this is just a number. If that makes more sense to you, then do it. You're going to get the same answer I do.
I would just the sine
So we're gonna go through all of this and we're gonna get a number, right? We have mg times all that stuff on the bottom there. And you're gonna answer for FT2, which is probably gonna be 431 newtons. But try on your calculator to double check. Yeah.
I got the 300.
Oh, is it 320? I'm off. And I've run out of board space.
No way. I'm still hung up on 22.
What does it take? 320?
I got 319.8. Put it I got negative, raise negative 9.8 meters a second squared.
Shouldn't be. So Jake brings up a good point. So I know you guys are scrambling to copy this down, and we're only 2/3 of the way down the question.
Great.
When we do the math here, right, when you put G in, G is just the magnitude of gravity, so it only goes in as a positive number, because the vector part of gravity, because we all know it's going down, we already determined that when we put this negative sign here. So there's where the negative comes in for its direction. Okay, so you don't use negative 9.8, so you'll get a positive tension there. For the last third of the question, we're going back to equation 1, because the question is what are the tensions of the rope, right? So we only found one of them. The second one is easier to find because we just used equation 1 with the numbers that we know to get the answer. Got 430. What's the real answer? I have 431.
430.9.
I'm gonna stick with points. Okay. So your therefore statement would say therefore the tension of the ropes are 431 and 320. So that obviously is not very easy. Not all our questions will be this complicated. Actually, this is on the harder side of what we do. It's a process that I know for this one uses skills we haven't used yet in our course. So I just want you to take your time and go through it. On the slideshow, and if you do print off the examples for the unit, if that's something that you do, I do have 4 questions, a 1-word problem and 3 picture problems that covers this just practice of the same thing. So the first one here is the easier version because the angles are the same. This one is exactly like what we just did. So is this one, and then that's just a word problem that covers the same stuff. So, yeah, that is your homework. Yeah.